Okay, there's a couple phrases that it would be really helpful to know. Okay, so the first one is, how do you interpret the phrase proportional to? Like, what does that mean? Proportional to. Mathematically, how do you write that? Well, if I said force is proportional to acceleration, that means the force is something times acceleration. Or if I say that momentum is proportional to velocity, then that means P is something times V. See? So when I say that the oil rate is proportional to the oil, you can think of that as the volume of oil, the rate of that is something times the volume of oil. See? So the rate at which the oil is changing is equal to something times the amount of oil at that moment. And since we don't know what the proportionality constant is yet, we just typically put a K here. Okay, so this is the first one. I kind of gave it away. But the phrase oil rate is proportional to oil would be written like this. Okay? How about the next one? Give the next one a try. Okay, so this also has that is proportional to phrase in it. By the way, if you see is directly proportional to, that's the same thing as is proportional to. So, okay, so this one also has an equals K times, but it's different on each side. It's not dV dt, it's what? Yeah, the rate of change of temperature, right? So you can use like a capital T for that. The rate of change of temperature is proportional to. Now what is it proportional to? Sounds like a more complicated quantity this time. What's it proportional to? What does it say? Yeah, it's a difference of two things. The difference of two things. So what did you guys end up putting in the blank here? Something minus something, right? What did you put, Mimi?
I put capital T, like O, and then capital T, T, bracket.
Like this?
Yeah.
Okay, so it doesn't really matter what you call the temperature of the environment. Some people call it T sub E, some people call it T sub S. Where E stands for the environment, or S stands for the surroundings, whichever. But don't put T naught. T naught would be the starting temperature. We want this to be any old temperature, the current temperature of the object. So the temperature at any time. So I'll just put E and V here, so there's no way you can miss what that means. Okay, it's a little more complicated, but it still has that is proportional to feel to it. Okay, before we leave these two examples, you should know that this is the diff EQ. That goes with this sentence, okay? And this is the diff EQ that goes with this sentence. And these are not the actual solutions. You cannot use these to find volume or temperature. They will not help you find volume, they will not help you find temperature. What are they for? Volume rate, temperature rate. That's what they're good for. Now, if you try to separate variables, so that means you divide by V, you multiply by dt, and you kind of separate the dt's to one side and the v's to one side, you can actually integrate everything and come up with a general solution. And the general solution for both of these is predictable and should be memorized. So anything that looks like this, you should just memorize it. This will come out to V equals V naught e to the kt. And this will come out to T minus T environment equals T naught minus T environment e to the kt. These two are worth memorizing. These black general solutions go with these blue differential equations. Okay? So when you memorize this sort of thing, memorize it as a package deal. I explained this before. Memorize the sentence structure, the equation structure, the EQ, and the general solution structure. The more of these you can memorize, the easier diff EQ is going to be for you. What I didn't like about diff EQ time on the test to rederive, do I? So, then the same is true for us. Both of these general solutions take quite a while to derive from the blue. It's not worth our time. Okay, notice the similarities. This is V and KV, see that? And this is just V equals V not V to KT. This has the exact same structure as that. The only difference is the left side's a little surprising. But think of it as the current difference between the temperature and the environment is equal to the original difference between temperature and environment times E to the KT. So the same way that the current volume is the initial volume times E to the KT, here the current temperature difference is equal to the initial temperature difference times E to the KT. So these are very much alike. Okay, let's look at the next one. I kind of gave this one away a few minutes ago. I said that G equals negative 9.8 is a differential equation. Can you write this sentence as a differential equation? The downward acceleration is 9.8. The downward acceleration is 9.8. How would you write that as a diff EQ? This one doesn't use the is proportional to phrasing. So most people wouldn't word it this way. We would say the acceleration is negative 9.8 is probably what you would say. And who writes meters per second? Just meters per second squared. How do you write that as an equation, though? A equals negative 9.8, but that's not a diff EQ. It doesn't look like a diff EQ, right? What's one way to re-express A? The second derivative of what? X, okay. Where X is like position, maybe? Yes, we could do that. So if the object's falling, I might tend to use Y, not X. You know what I mean? Because you're measuring Y's vertically. The object's falling. So d squared Y dt squared is negative 9.8. What's another way to think of acceleration? Acceleration is the second derivative of position. Isn't it also the first derivative of something? Yeah. So you could also just write dv dt. So another alternative answer to this would be dv sub y dt equals negative 9.8. They didn't say if they wanted us to write a second order or a first order answer. They did not clarify that. In the first equation, if you wanted to solve for y, you would need to integrate 2 times. In the second equation, if you wanted to solve for v sub y, you only need to integrate once. Okay? Let's look at the next one. When a valve at the bottom of a water tower is opened at a rate, the rate at which the water level changes is proportional to the square root of the level of water in the tower. Express the rate of the water level as a differential equation. I think you're going to have one of those something dt is equals k times something here. Right? And for those who just showed up, I already recorded the first few, so you can always check them out on the video. Okay, how do you write the rate at which the level is changing? How do you write the rate at which the water is changing? Something dt, right? How do we normally measure water in a water tower? If the water is in here and the water is draining out, what's a great way to measure the water? the height. Yeah, you could call it volume if you want, but it actually says the level of the water, right? So level of the water is probably more like H. Does that make sense? So I wouldn't put V dt, but maybe D H dt. Does that make sense to you guys? The level is H, okay? Finish it up there. It's proportional to what? Square root of the level of the water. So what is the square root of the level of the water? Audrey, what's that?
Isn't it the square root of?
Yes, this is the differential equation. So what still remains unknown is k. So what a scientist would do would be that if they had this little model, they would probably get k just by dividing by rad h on both sides, move the dt over area both sides, and they get an equation, and then they try to fit their data from their tower into this and get k figured out.
Oh, we already were.
All right, how about this next one? Flu epidemic spreads through West High. Population's 1,500. It's at a rate proportional to the product of the number of students already infected and the number of those not yet infected. So I'll let you think about that one. So this one's just significantly harder to think about, but basically you have a product. So there's that is proportional to thing. So there's definitely a dt here, there's a k here. The thing is there's a product here, okay? And then it's just basically those infected, those not infected. Well, those infected is P. It says in the instructions that those infected is P. Those not infected would be what? The rest of the students, right? So you don't want to invent like a new variable, right? You don't want to put like n or whatever for not infected. You need something in one variable. So let's just assume it's 1,500 minus P, those not infected. Okay, you got the right side figured out. So what is this the rate of change of? So it says here what? The flu epidemic spreads at a rate. So it's d something dt. What is it? What? dp. Yes. The rate of change of those infected is proportional to the product of those infected and those not infected. Does anybody recognize this? Recognize this? No? Yes. Recognize it, Brian? This
I
equation?
remember the equation set up like that.
Mhm.
It was, I forgot what it was called, but we learned it like,
We did. This is called logistic growth. Logistic growth. KPM minus P. What does the 1,500 represent? The boundary. It's the carrying capacity. Okay? So when I first taught logistic growth, I never taught this phraseology. Like I never explained that dp dt equals kpm minus p. I never told you that it was the rate of change of a quantity is proportional to the amount of quantity that has changed versus not those that hasn't. You know what I mean? I never said like it was a product of anything. I just gave you this equation. I told you how to sort of interpret it. I told you to look for m. M is clearly 1,500. It's like a theoretical maximum of those that could get infected. I told you how to write the logistic growth population equation. So let's go ahead and do that real quick. This one, if you ever run into a situation like this, it gives you this general equation. I think I did my generals in black, right? So it should be P of T is m over 1 minus, or 1 plus, a e to the negative market. Maybe you remember me saying market, or negative market, which is really weird. But mkt reminds me of the word market for some reason. Does anybody remember this equation? Okay, this is the general solution to this differential equation, and if you plan on not memorizing this, good luck going from blue to black. I gave you the blue to black derivation, and it takes an entire page of typed equations. Okay? So it's a lot of work. Everybody memorizes this one. This is logistic growth. Memorize the sentence. It usually does have to do with flu spreading. geometry of growing in a confined environment, a capacitor charging in a circuit where it can't charge beyond 1 farad. Okay, so logistic growth and its diffie Q. All right, memorize that. Tough one to think about though if you're just kind of guessing at it. How many of you got the diffie Q right? How many got close? How many didn't know it was dp dt on the left? Okay. Let's try this problem now. So this is the next page, right? Did I skip a page by accident? This is correct, right? Okay, cool. Sometimes I push a button and I jump like 3 pages. This is a perfect segue into this problem. So this is talking about wolves in a certain environment, and it doesn't say that it's logistic growth, but you would expect if you threw wolves into an environment, the population would grow according to logistic growth. Let's see if we can make sense of the sentence and write the diffie Q. That's like not even part A yet. But can you write a diffie Q first? Just put your answer up here somewhere. It's not part of your answers. But we need a diffie Q. Maybe it's logistic growth, maybe not. Let's see. Okay, this one says that the population rate, that's dp dt, is directly proportional. How do you write that? Equals k times. It's proportional to what? 800 minus p. You don't need the of t. Wait a minute, this isn't logistic growth. It's missing a p. If this was logistic growth, there would be another p here, but there isn't. Okay, so be careful not to assume anything. Read the sentence, write the diffie Q. So what's going on is this environment doesn't have a theoretical maximum. What's going on maybe is that this environment is flexible and can allow, more animals, or it's not necessarily a logistic situation. So it's not the kind of environment that can only support a certain amount of wolves. Okay, anyway, this is what they gave us. I guess we're just going to have to try to figure it out. Now, it says P of 0 is 500. That sounds like an initial condition. Well, you don't use an initial condition until you have a general solution. This doesn't get used until we isolate P. So what we need to do is do separation of variables. We need to move the dt to the right. We need to move the 800p to the bottom. And I really don't like the 800 minus p look. So I'm going to actually write it like this. dp over p minus 800 equals negative k dt. So what I did was I factored out a negative. So this was a negative k. And I moved the dt over. That way, since I'm going to be integrating, I'd rather integrate p minus 800 than 800 minus p. I don't want that chain rule. So I'll just show you what I did here. I just basically switch this around before dividing by p minus 800. Okay, time to integrate. So first we separate, then we integrate. I'll write that on the side. Separate, integrate, and now we anti-differentiate. Anti-differentiate. Okay? So this is not a hard integral. How do you anti-differentiate 1 over anything linear? 1 over something linear like that. ln, right? Okay, good. So this is just ln, absolute value, P minus 800. What's the antiderivative of 1 dt? I left the negative k outside, I hope you don't mind. What's the antiderivative of 1 dt? It's just t, right? So this is just negative kt. I would like to isolate p, that's what they asked for. Don't forget the constant of integration.
We don't have to
Yes.
go plus C on these.
Oh, sorry. You're right. I almost forgot. Choose one side and put a plus c on.
Okay, and since K is a constant, do we need to, will that affect C at all?
No. Remember, c is not just a constant, but any number we want. Any number we want. Okay? The antiderivative of negative kt, I'm sorry, the derivative of negative kt plus 1,000,000 and the derivative of negative kt plus 14 is exactly the same. It's negative k. So this can literally be anything we want. You can call it kc if you want. Are you wondering if we should distribute the k or something? It wouldn't matter. The c can literally be anything. It can include the k, not include the k. The negative, it can be positive, it can be 0 for all we care. We're actually planning to find c, and this is actually a good time to do it. Before we e both sides and get the c buried hopelessly somewhere, why don't we find c right now? Right? We know what time is, we know what the population is. So this is the next thing you do. You've separated, you've integrated, you've anti-differentiated. Now you're going to plug in 8. I just want all my words to end in 8 here. So you're going to separate and integrate and anti-differentiate. Then you will plug in 8. And then finally we will isolate the p. But we're going to wait until we have our c figured out. So let's find c right now. Okay, so plugging in time 0 and population 500 gives us this look. In other words, c is ln 300. Did everyone get that? ln 300? It's technically ln of absolute value negative 300, but that's just ln 300. So we separated, integrated, anti-differentiated. We pluginated. Now it's time to isolate. Okay, so now we know our particular solution was ln p minus 800. And this used to say negative kt plus c, but we now know it's an ln 300. So we don't need to be ambiguous about c anymore. Now it's time to isolate p. So we'll e both sides. P minus 800 equals e to the negative kt plus ln 300. And then we'll add the 800 over. Can anyone see a way we can kind of simplify the first term here? What's a way we could simplify the first term? We have e to the something plus something. Is there another way to write that? Separate it into e to the negative kt times e to the ln 300? That's a good idea. Let's do that. So that'll just make it look a little bit nicer. E to the negative kt times e to the ln 300. Wait a minute, what's e to the ln 300? Isn't that just 300? Ah, okay. So this is so much nicer. I'm glad we did that last step of simplifying. This is just 300 e to the negative kt plus 800. So step A on this problem was kind of a doozy. It's a long process that involves at least 5 steps. Separate, integrate, anti-differentiate, pluginate, isolate, and simplificate. Okay? So there's your population model, though. That's awesome. Now you can use it to do part B. It'll take you 2 seconds. Okay? We do need to find K. So we're going to go ahead and plug in 2 for time, 700 for population. So 700 is 300 e to the negative 2k plus 800. Why don't you take a moment and solve that. Don't expect a friendly value for k. It's usually some ugly decimal. Okay, so subtracting that 800, you have negative 100. You're going to divide by the 300. You're then going to ln the answer. And I messed that up somehow. Yeah, something's fishy here. Did I forget an absolute value somewhere? Oh, I know what happened. I know what happened. Right here, guys, see this? In yellow, this part, oops, that's called scribbling it out. I didn't mean to do that. This is p minus 800. I was going to highlight that. P minus 800 should have had an absolute value on that. This should have been absolute value, p minus 800. How does that affect my next step? I feel like I need to clean this up a little bit. You don't have to erase all of yours. You could probably squeeze yours in, but we do have a negative error here. How do you get rid of an absolute value? You can call it a plus or minus on the right. Okay, so p minus 800 is plus or minus e to the negative kt plus ln 300. Which one should we trust? Positive or negative? Should we call it positive or negative 300 e to the negative kt plus 800? Which one's correct? So this is where you might need to actually look at your initial condition one last time. Okay? We use the initial condition to get the c value, but we're not quite done with the initial condition until we've chosen between plus and minus. Okay? So which makes more sense? If we plug in 0 for t, this is going to become a 1, right? So I'm going to plug in that initial condition one more time. They told me that this will be 500 when time is 0. Which statement makes more sense? To say 500 is 300 plus 800? Or 500 is negative 300 plus 800? Which one's actually the true statement? The negative. The negative actually makes sense. The plus actually doesn't make sense. So we're going to actually vote. We use that initial condition twice, see? We're going to actually vote on a negative right there for our model. So our model actually has a minus 300 right there, and hence a minus 300 in part B. As we started out the problem, we started off with the wrong assumption there. Okay, that's been fixed. Let's go back to our calculator screen. It should have been subtracting the 800 gives me negative 100. Then we divide by negative 300. There we go. Then we try to ln that. And then we divide by negative 2 to isolate it from that k. 0.5493, blah, blah, blah. And I would recommend that after you copy this down, or even before you copy this down, store it as alpha k in your calculator. Because you want that thing to be super accurate. You don't want to round that ever. So store it as alpha k. But you can kind of come down here now and write your answer to the nearest thousandth because they'll accept it. Whether you truncate around, it's 0.549. Okay, so how did Mr. Short catch his mistake? I had some trouble doing ln of negative 1/3. It didn't work. And that's when I realized, oh, I forgot. My initial condition forces me plus and minus. And I did kind of ignore that opposite value, didn't I? Okay. All right, let's now find the limit as t goes to infinity of p of t. Oh man, does that mean we have to do a big old L'Hopital's rule or something? Does anyone know the answer to this question without doing any work at all? What do you guys think?
Wouldn't it just be 800?
Okay. Why are you saying that?
Because it's a carrying capacity, and it's asking if time goes on forever, what's the maximum for population growth?
Right. So basically, this isn't logistic growth, so you probably wouldn't call it carrying capacity, maybe.
Yeah.
But this term is going to vanish when you make t large because of the minus power there, and k is a positive, right? So this is just going to vanish and you get 800. So logically speaking, 800 wolves is the most there ever could be as the population grows towards 800. So there is a maximum. It's not a logistic curve, but there is kind of a carrying capacity, I guess you could say. How would you show your work here? I'm not sure you need to. I think you should put units on here, 800 wolves, but I don't see any need to show any work. I can't imagine we'd mark you down. So what year of test was that? 1993, AB6. The only difference between 1993 and 2015 is now they expect you to use your calculator to do more advanced things. You see, back in this time, in 1993, the graphing calculator was first being invented. I had one. I had a Casio, 7800, I think it was. Some of my students have it, but it's a little outdated model. In 1995, they made the AP test require graphing calculators, like you couldn't do without the graphing features. But notice this problem did not technically need anything except a scientific calculator. That's because of the year. But now they've upped the ante a bit and expect you to use like other features, if that makes sense. Okay? Any questions on that? Now they actually want us integrating on the calculator screen and all that, right? Okay, but still an excellent problem. From reading the question to writing a DiffEq to the 5-stage process of getting the general solution, or a particular solution. Okay, slope fields usually is pretty easy for people, but every now and then there's a student who just doesn't get it. So let's just review this real quick. Just think of this as the slope is x minus 1. So I was teaching this to a student last night. I was tutoring. He did not understand this at all. But then when I told him it means the slope is x minus 1, he felt like he should pick an x. I said, yeah, pick an x. What do you want to pick? He said, let's pick x equals 0. So what would this slope be if x was 0? Negative 1. So I asked him to draw the 6 points that would represent, and that would be all of these. And he's like, oh, I get it. Now I'm going to pick x equals 1. Right? Okay, so I told him you got to make them all look parallel. You're not allowed to use a ruler. Don't make them too short and don't make them too long. Make them straight and don't hook them. I told you guys all the same things, right? So make sure they all look exactly the same, that they really look like they're slope negative 1. Don't make them too long, don't make them too short. Okay, it's a slope field. What happens when x is 1? When x is 1, slope is 0, so that'd be all of these. Draw them as horizontally as you can, freehand. Not too short, not too long. Make them straight. Make them parallel to each other. What if x is 2? Slope would be 1. Right? Try to make them all look like they have a slope 1. What about this little dot in the corner? Should I do that one too? What about this guy? You think I should draw one there? Yeah, x is 2. Listen, if you miss one of them, it's a 0. Like, they will dock you all the points if you don't finish this thing. You can't just say, oh, I think they get the point. No, fill in the whole thing. Every single dot gets a hash mark. So you still got another 12 to do. When x is negative 1, the slope is negative 2. Just do your best. When x is negative 2, the slope is negative 3. So these are getting really steep. And it's getting tempting to get sloppy here. That's the slope field. Now, if the equation is simple enough, you could just integrate both sides, and you'd be like, oh, I get it. It's just 1/2 x squared minus x plus some constant. So these are all basically parabolas. See? They're all parabolas. Don't draw this part. A bunch of parabolas with unknown vertical shifts. See? That's what they are. So we call this a family of curves. The red is called a slope field. And the general solution is this thing in blue up here. And these little curves might be particular solutions. But that's going beyond the question on this one. On this next one, you probably wouldn't pick x's. You'd probably pick a what? A y, right. So the slope is half of y. So like if you pick 0, if y is 0, then your slope is what? 0. So these, all of these would be horizontal. If y is 1, the slope is what? Half, right? If y is 2, the slope is 1. I just wish I had a ruler. If y is 3, the slope is 1.5. That's getting awkward to draw. If y is -1, the slope is -1/2. And if y is -2, the slope is -1. I always love doing the last row because I feel like I'm almost done. Boy, those don't look like parabolas, do they? If you sketch in a few blues, what shapes do you think they would be? I mean, look at the diffy-q's. They look almost the same, right? That one says dy dx is x, basically, and that one says dy dx is y. Shouldn't they just be like the same shape, maybe sideways? Not at all. Okay? This, if you draw sideways parabolas, those aren't even going to fit the mold here. These are parabolas, these are not. Does anyone know what shapes would fit nicely in here?
It looks like it'd be like a volcano.
Okay.
So that's
Very good. Okay, so really know, you would divide both sides by y. You move the dx over, see? They're actually exponentials. E to the x, 2e to the x, 3e to the x, 4e to the x. See? Negative e to the x, -2e to the x. So it's a totally different family of curves, even though the diffy-q's look so much alike. Another reason why diffy-q's a hard class. The next one, should I pick an x or a y? Both. Right. So this is where it can get pretty challenging. There are some things that are interesting, like right here, guys. If x and y are the same number, what do you know? We can make this go pretty quickly. So I'm trying to teach you some tricks. If x and y are the same number, what would your slope be? 1. Oops. So if x is 1 and y is 1, if x is 2 and y is 2, if x is -1 and y is -1, if x is -2 and y is -2, I don't think I should do the 0 case. Probably shouldn't fill in a mark here, right, guys? 0 over 0 isn't technically 1. Okay, we'll skip the 0, 0, but we just got 4 of them right there. What if x is 0? If x is 0, what would that give you for a slope? 0. So that means these are horizontal tangents. Still not too comfortable with that origin point. Not too sure what to do with that guy yet. So I just basically gave you 9 of them without doing any real calculations. What if y is 0? Undefined. Vertical tangents. I don't think we should fill in that origin. So I called Mr. Lynch and I said, on a slope field, what do you think we should do about x over y when y and x are both 0? And he's like, just leave it blank. So he said, don't even fill that one in. Okay? It's some kind of a singularity point. It's indeterminate. 0 over 0, we don't even know what that means. So you we'd have to solve the diff EQ and figure out if 0, 0 is a vertical tangent, or is it a horizontal tangent, or is it just totally empty? Is there like an asymptote there or something? If you see my point. So, probably not an asymptote, but now you have some more to do, but I've got you, mostly done with it. So, you actually now have to find, like, plug in 1 and 2, So this guy, I'll do these in blue. If you plug in 1 and 2, this is a halfer slope right there. See? If you plug in 1 and 3, it's a 1/3 slope. If you plug in 2 and 3, it's a 2/3 slope. Two-thirds slope. That's kind of hard to do. So I think I should connect this point to this point. So basically like that. It's getting hard now. If you plug in 2 and 1, it's a 2-sloper. If you plug in 2 and -1, it's a -2-sloper. If you plug in -3 and 1, it's a -3-sloper. If you plug in 1 and -1, it's a -1-sloper. If you plug in 1 and -2, it's a -1/2-sloper. This was just awkward, right? So I'll let you fill it in later. But actually, the diff EQ is not that hard to solve. Okay, you can see on the next page. Oh, by the way, I want to show you something real quick. Sorry, guys. Look at this. Remember I told you about wind plot? Under equations, differential equations can be plotted. There it is, dy dx. We want x over y. I love this feature of wind plot. Bam, there's the field. Notice that the computer didn't even plot the origin. The computer didn't know what to do with it. It didn't know about any of these. These are all vertical tangents. It didn't know what to do with those. Graphing software typically doesn't handle vertical tangents very well. But that's sort of like what we do. It wasn't too bad. How do we do? Get in there. Okay, I've never seen them ask you to fill in 25 dots. Okay, the most I've ever seen is maybe 16 dots. Okay? But that's a cool feature of WinPlot. Remember, WinPlot is a free download and it doesn't even install into your computer's registry. It just unzips as a zip file. So it doesn't intrude in your computer privacy or anything. It's great little software. And it's a small download. Just Google "Where's my peanut" online, and that's how you'll find it. You can download WinPlot, but it's a little hard to find it on your hard drive. So after you download it to your hard drive, if you don't know where you unzipped it, Google "Where's my peanut," because peanut is the name of the folder it will create on your computer. And many people have wondered where the peanut was. And it's actually, the problem is it does install it to your C drive, like to the C root directory, so it doesn't install in the registry, but it does install the folder in a strange spot. So, okay, let's go to here, matching. You guys are probably good on this, so we can skip over it. It really is pretty simple, especially if you just think qualitatively, like, if x was 1, what would happen? And then search the graph. Let's go down to some real questions, So, oil is being pumped out continuously from a certain well at a rate proportional to the amount of oil left in the well. Ooh, they were very nice to us. Look, they gave us the diff EQ. They interpreted their own sentence for us. Beautiful. Initially, there was 1 million gallons. 6 years later, there were 500,000 gallons. It will no longer be profitable to pump oil when there are fewer than 50,000 gallons remaining. Write an equation for y. So it sounds like we're just going to solve the diff EQ first. Okay? So why don't you guys give that a try. Try to get y by itself. So you will isolate, integrate, anti-differentiate, plug in a isolate. So separate, integrate, anti-differentiate, etc. so just to kind of get the ball rolling, did you guys write dy over y equals k dt? Okay, so that's separate. Did you integrate? Okay. Did you anti-differentiate? Did you get ln absolute value y equals kt plus c? Okay. Did you pluginate? Meaning you plug in the initial condition. There were 1 million gallons when the time was 0. How many of you put in ln a million equals k times 0 plus c? Anyone do that? Okay. So I'll pause again, let you keep working. So c is ln a million. So ln absolute value y is kt plus ln a million. E both sides. This time I'm not forgetting my absolute value. Last time we saw that you can separate this into e to the kt times e to the ln a million. In other words, this is just absolute value y equals a million e to the kt. And then we can decide if we want it plus or a minus. So which makes more sense? If I plug in a time of 0, am I going to get y equals a million or y equals a negative 9? Which one makes more sense? According to the instructions. Yeah. In this problem, it's the positive that makes more sense. So we won't need the negative. But again, you have to think about that. Last time it was the negative that mattered, remember? Oh, shoot. We could have done this without any work at all. Remember what I told you? This is such a familiar diffie-q, you should memorize its general solution. Anything that's of the form d something dt equals k times that something is always that something times the initial something times e to the kt. So you could have just jumped straight to the answer. That thing is uninhibited growth. That's y equals y not e to the kt. Y equals y not e to the kt. What a waste of time. So on the AP test, we're not going to waste that time. We're going to jump straight to that solution. You can write a brief sentence if you like, if you think the graders won't like it. But you can just write, the general solution to this uninhibited growth is blah. Just spit out the answer. They'll take it. If you defend it, they'll take it. They're reasonable folk, most of them. Okay? So I feel like we wasted some time. At what rate is the oil in the well decreasing when there are 600,000 gallons of oil remaining? There's one problem. We don't know K yet. How can we get K? Somebody raised some work here. Just keep my answer. But how can I get K? I can't really proceed without it. Without K, I can't really do much else with this problem. In fact, come to think of it, I don't think they want this answer with K in it. We're not quite done with part A. Does anyone have any ideas how we might get our K figured out? What?
Set y equals 500,000 and t equals 6.
Yeah, we never use this data. I don't think you should plug in the 0 and the million again, but you can plug in the new data here, namely that this is 500,000. At the 6th year. Yeah, okay, so let's get our K figured out. You divide by a million, that's a half. Right? So you've got 500,000 divided by a million, that's just 0.5. Then you're going to ln the answer. So ln 0.5, basically. Then you'll divide by 6. And store this in your calculator as alpha K. If you need it later, you'll have it. Okay, so I think we should update our answer. How about y equals a million e to the And then KT, let's write negative 0.116. That's a better answer for part A anyway. More specific. Okay, part B. At what rate is the oil in the well decreasing when there are 600,000 gallons of oil remaining? Oh no, now we have to take the derivative of our answer maybe? Do I have to take the derivative of this now so that I can get an oil rate? Oh shoot. Don't have to, it's right there. Okay, so now what you have is the oil rate equation and the oil amount equation. See? There's two things we know now. Believe me, I've done it. I've taken the derivative of this again, only to find out it brings me right back to here. Okay? So we already were given the derivative equation, and we know K now. We're just going to plug in 600,000 for Y. So dy dt is negative 0.116 y. That's this green equation up top, updated with the y with the k inserted. See? Let's just plug in 600 grand and see what happens. We want the rate, right? So we're going to plug in 600,000. So in my calculator, I'm going to type that as 600,000 K. So what is 600,000 K? Okay, the answer is negative 69,314.718. So dy dt is negative 69314.718. I think we should give this some meaningful units, right? This equation over here is measured in gallons. What do you suppose dy dt is measured in? Gallons, what, per year. Notice that it's dy, which is a change in gallons, over dt, that's a change in years. So that would be appropriate units there. Boy, that's a big number. What does that mean? There is only one instance in the history of this water tank, or oil tank, oil well, where there were 600,000 gallons. And at that very instant, this was the rate at which it was dropping. Okay? So, what's weird is 1 minute later, this rate changed. But that's like the instantaneous rate, I guess, right? Part C, in order not to lose money, at what time should oil no longer be pumped from the well? So, it said here that it would no longer be profitable to pump oil when there are fewer than 50,000 gallons remaining. So 50,000 gallons. Should I plug that into the gallons per year equation or the gallons equation? 50,000 gallons. Which one should I probably plug that into? DFEQ or the general solution? Or table solution? Yeah, this is a measure of water left in, or oil left in the thing, right? So I think it makes more sense with the 50,000 right there. Yeah, and then we'll try to isolate T. This will not be hard. Any pre-calc student could do this one. So you're basically putting 50,000 here equals a million e to the negative 0.116 t. And you're going to try to solve for t. So you can do 50,000 divided by a million. Divided by a million. Obviously that's just 0.05. Then you're going to ln that sucker. Then you're going to divide by k. I've already got stored in the calculator, nice and accurate here. 25.932 years. 25.932. And it occurred to me, I should probably be using squiggly equal signs on just about everything here. I've heard that they're a little strict about it. Anything that's got a decimal in it, go back and change them all to squiggly equals. So after 26 years, they need to either refill this, or they need to either drill a new well or something, because it costs a lot of money to pump oil out of a well, and they've decided that once they get down to 50,000 gallons of oil down there, I don't know, they're either sell that well or go dig a new one. It's just not worth the money to pump it out anymore. Makes me wonder if there's like oil reserves underground that no one ever pumped out because it wasn't worth their money. You know what I mean? Makes you wonder. These are typically pretty accurate from a business standpoint. So these guys write questions, they do a good job of it. So this just goes on and on, right? I mean, this packet's huge. I don't know, how many more should we do here? We can just kind of take a glance here. This is a cool one. It's a skydiver falling, and her velocity satisfies this differential equation. Use separation of variables to find her velocity. This one is an FRQ where you had to sketch a slope field. Two of them, in fact. Let's look at logistic growth, though. So you can have fun with those other ones. The skydiver one's pretty cool. You've probably wondered about skydivers and terminal velocities and stuff. There's your problem. That one will teach you something new, I promise. That's a fun problem. Let's talk about logistic growth for our last 10 minutes here. So in exponential growth, we would assume that the rate of increase or decreasing is directly proportional to population. So that's the whole dp dt equals kp thing. dp dt equals kp. This is called exponential growth or uninhibited growth. Sometimes it's a decay. Where something is allowed to actually decay all the way down towards zero. So I should have written that, I'm sorry, under how do we write this fact. Yeah, so this was supposed to go here, sorry. Okay, however, in many situations, population growth will level off and approach a limiting number L. This is called the carrying capacity, and this is because of limited resources. In this situation, this rate of increase or decreasing is directly proportional to the product of P and L minus P. This type of growth is called logistic growth. How do we write this with calc symbols? This is the one where it's dp dt equals k times P times L minus P. It's almost like this is a sort of an afterthought, you know? It's like just kind of multiplied on there. And what it does is it keeps everything under L. Okay? Now logistically, the logistic graph will look like this. There will be a starting population. That's not zero, by the way. It's P naught. Okay? It could be zero. But most likely it starts with an initial population, P naught. Make that a little more obvious. So there's a little gap here at the bottom. And then this thing will grow towards some theoretical maximum L. Okay? So when does the population grow the fastest? Well, that's like saying, when is dp dt max? This is like asking, when is dp dt maxed out? Well, dp dt will max out when d double prime of p, or p double prime reaches zero. So you're looking for an inflection point, basically, on this picture. Where is our inflection point? It's right about here. Right smack in the middle there, maybe. So there's two ways to understand this question. When is P growing fastest? One is it's saying, when is dp dt maxed out? So you're looking for a point of inflection. Or two, there's lots of tangent lines on here. Which one's the steepest? It's the same question. Well, that's the one at the inflection point. So the steepest tangent line occurs right there. Does anybody remember at exactly what value that is at?
Half of the
Half of the,
limit, yeah.
right. So what happens is the system is being populated, and then when you reach half capacity, things start to slow down. So this always occurs at L over 2. When the population reaches half the maximum, the graph changes from increasing at an increasing rate to increasing at a decreasing rate. Either way, it's increasing, it's climbing the whole time. But here it's increasing like exponentially, and then here it's not. You see? It's almost like the system realized, hey, we're reached half capacity, we better start slowing down here. We're going to run out of resources. So that, the bears all keep getting like, can't have too many more babies. So we're going to go over, we can't increase at an increasing rate forever. At some point, it's got to peter off. So this happens at half capacity. Now before you get too shocked and say, gosh, is that always true? I'm pretty sure logistic growth was designed with this in mind. I think it was designed to decay, or the growth rate decays off when you hit L over 2, so it's not like magic. This is just how the logistic models are designed. Okay, pretty sure. I'll have to research. Is this L over 2 by coincidence, or is it that these FAQs are designed that way? I have to look that up. But, so anyway, there's your curves. And so sometimes all you do is they'll say that the L is 500, and they'll say, when does it grow the fastest? They'll say 250. Like, that's not even hard work, right? Okay. So let's move on a little bit further down here. Whoa, what is this graph? What is going on here? Does anyone know what's going on here? Yeah, so what's happening is, let's say that these are, I don't know, let's say that there is a certain cage that can support 30 butterflies, okay? There's enough resources for 30 butterflies. And some Joe Schmo comes in and puts in 5 butterflies, okay? Comes back a couple of years later, finds out, maybe after, 15 years, that they've reached the point of inflection. There are now 15 butterflies, and things need to start changing in this environment. We can't have the butterflies increasing at an increasing rate anymore. They've got to start slowing down. So things sort of inflect, and then the growth rate starts to decay off. Okay, you still reach at 30, but it's doing so at a decreasing rate. Okay, this is a different scenario. Joe Schmo brought in 15 butterflies and put them in this capacity. He brought in half capacity butterflies. You see? So there is no increasing at an increasing rate. That doesn't happen. He brought in half capacity. It's going to decay right away. I don't mean fall down. I mean the tangent lines decrease only in their slope. Here's a really wise zoologist who brought in, or entomologist, he brought in 25 butterflies and stuck them in a cage that only supports 30. He's not going to see any growth at an increasing rate either, right? He's already above half capacity. Here's somebody who brought in 30 butterflies and put them in an environment with 30, where 30 butterflies can be supported. What happens to the population of butterflies? It doesn't change. Okay? So this is all theoretical, of course. Some butterfly might have a baby or whatever, but then one's going to die. It's going to balance out. So this environment only supports 30 butterflies, new or old. Okay? What's going on here? What's Joe Schmo doing? Bringing in too many butterflies, right? So Joe Schmo brings and puts 40 butterflies into a 30 butterfly cage. What happens? 10 of them die. Over time. Right? Or maybe some are born, but a net of 10 die. This system has to decay. What happens if he brings in 50? He's more than 1.5 carrying capacities up. Should decay rapidly, right? The system can't support it. Does this graph make more sense to you now? Okay, so this is several scenarios of what's happening. Based on this graph, what is the carrying capacity? 30 butterflies, obviously. What happens when the population introduced is less than L over 2? Well, we start out with growth, rapid growth, Okay, so if you want to fill this in, you could just put 30. What happens when the population introduces less than L over 2? The graph, or the population, will increase at an increasing rate until L over 2, then increase at a decreasing rate. But that kind of phenomenon only happens if you bring in less than half capacity, which is only this bottom curve, really. It's the only one with the point of inflection you consider. It's the only one with the point of inflection, isn't it? You should have seen something like this in your science classes, but that was before the language of differential equations was introduced. Okay? All right, we have about 3 minutes left. Here's some more questions. What happens when the population introduced is between L over 2 and L? So that would basically be this curve here. This only increases at a decreasing rate. So population will only increase at a decreasing rate. What happens if you introduce a population equal to the carrying capacity? The population rate will be 0. What do I mean the population will be 0? No, I didn't say that. The population rate will be 0. The tangent lines are all horizontal, right? So that's this drawing up here, the flat line. What happens when you introduce a population greater than L? We have instant decay, right? So population rate will be negative. Population rate will be negative. That's the same thing as saying the tangent lines will all be negative. Okay, let's do in our last 2 minutes this quick bears problem, which I already did in the notes a while ago, back in the end of chapter 6. But this goes real fast, especially when you're comfortable with it, and you can read these. So it's always nice when they give you the diff-EQ in already the right form. So they're actually writing it perfectly factored for us. This is K, folks. This is P. This is M minus P. It's beautiful. For extra practice, look at my test I gave you. When I gave you the test on this, I had it all foiled out, and you had to refactor it. Okay? I distributed it just to mess with you. But they'll do it too. They'll do it on the AP test. But the point is, you can tell clearly what the carrying capacity is. There's no work to part A. What's the answer? 100 bears. Okay? Let's add that to our little graph down here. 100. Okay? What is the bear population when the population is growing the fastest? 50 bears. Right. This is the break-even point, right? I told you this problem's not much work. What is the rate of change of the population when it is growing the fastest? What is the rate? Do you think I should plug this into dp/dt or try to find a general solution? I think we can just plug it into dp/dt. Yeah, what is the rate? That's dp/dt. It's asking what is dp/dt? Oops, it's kind of crashing on me here. Okay. So it's basically asking what is dp/dt when the population is 50. Well, that should be easy. It's 0.008 times 100 minus 50. So basically 0.008 times 50. Oh, I forgot the extra p. There's 2 p's here. So there's a 50 and then a 100 minus 50. I'll just make sure you guys are awake. So it's 0.0008, 0008 times 2,500. Which I should be able to do in my head, but I'm a little too tired today. I don't know what my excuse is on other days. 2. 2? 2 what? 2?
Oh, you changed the amount of zeros.
Did I?
Yeah, you put too many.
Maybe 20? Too many zeros.
Yeah, one too many.
Oh, I have one too many zeros. So that means I need to multiply by 10. 20. 20? 20 what? Good. Yeah, watch your units. This is a dPdt. That's bears per year. What it represents is the slope of, it's the slope at that inflection point. It's the slope at the inflection point. See? So your curve looks something like this. And the slope at the inflection point is 20. The bears at the inflection point is 50. What year is it? I don't know. I don't know. I don't know what year it happened. To get that information, I would have to solve the Diffie cube. I would actually need to set up the m over 1 plus a e to the negative market, find a, and then figure out when the population is e. But they didn't ask me to do it, so I'm going to have that problem. Thanks for coming.